All right, hello again, everyone. First of all, as I'm recording this, we are officially more than halfway through with eLearning, so congratulations on making it this far. I think by the time this video goes online, we will have about 2 weeks left to go before the AP test, so hopefully you're all starting to see the light at the end of the tunnel, and hopefully you're all starting to feel more or less ready for this. All right. So the problem I'm going to discuss today deals with these two blocks, one sitting on a tabletop, and the two blocks are connected with a string which is draped over this pulley here. This is actually what we would call a modified Atwood machine. Anytime you have two or more blocks connected together with a string or rope and there's pulleys involved, usually that's some kind of Atwood machine. All right, so we have a number of different questions to deal with here. A lot of them are really qualitative only, but there is some quantitative stuff towards the end. So this is a perfect example of a type of FRQ question that you're going to see. All right, so let's go ahead and look at part A here. Part A, first part says, suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. And we're told that there is negligible friction here, first of all. And there's negligible friction in the pulley as well. But we're also told that the mass of A is much, much greater than the mass of B. All right, so anytime you're asked to think about a situation where some quantity is either very, very large or very, very small, it's helpful to think about what would happen in the extreme limiting cases. So in this case, if we're comparing two masses, the extreme limiting case of mass of A being larger than mass B would be something like the mass of A being infinite, or equivalently the mass of B being 0. So if either of those were the case, then this system would actually not accelerate at all. So if we allow a mass of A to be much, much larger than the mass of B, the acceleration is going to be not exactly 0, but very, very small. So we can say the acceleration will be approximately 0. It still will move, but at a very, very low rate. Or we could say at least acceleration is much less than the acceleration due to gravity. And that's just to briefly explain our reasoning without equations. Just say that block A has a lot of inertia. So it will be very resistant to motion. All right, so A part 2 asks us to consider the other extreme, where the mass of block A is much, much less than the mass of block B. So again, here our extreme cases we could think about would be maybe like an infinite mass for block B, or maybe what's easier to think about is 0 mass for block A. So ask yourself, what would happen if A had 0 mass? Well, then there's basically nothing holding block B back from just falling. It's like there's nothing attached to block B at all, and you just let it fall. What would its acceleration be in that case? Well, the acceleration would be roughly equal to g. It would just fall under the influence of gravity. All right, and then the explanation there would be, block A has almost no inertia, so block B would just fall under the influence of gravity. Okay, so in part B, they want us to start thinking about the actual forces acting on these blocks. So now it says, assume that neither block is much, much larger than the other ones, but they're not necessarily equal either, so they both have two reasonable masses. And wants us to indicate the forces acting on each of the blocks. So let's let this one be A and this one be B. Well, block A is sitting on a tabletop, so there's going to be a gravitational force equal to the mass of A times g. There's going to be a normal force from the tabletop as well. Those two forces will be equal because block A is not going to accelerate in the vertical direction no matter what happens. But there is going to be some tension pulling it this way. All right. There's no need to draw a friction force here because we're told that there's negligible friction between A and the tabletop, so that's it. We're done for block A. For block B, we're also going to have a gravitational force. There's no normal force here because it's not sitting on a table, but it is attached to the rope, so the rope is going to pull upward on it with some force T. All right. Now, if we want to be technically accurate here, these two forces here should be equal in magnitude. They're both the tension forces in the same string or the same rope. What about the two forces acting on B? Should those be equal? Well, if the system is going to accelerate, then B is going to have a non-zero acceleration, which means the net force should be non-zero. So these two forces will actually not be equal. The downward force is going to be somewhat larger than the upward force, and that's what causes B to accelerate downward. So neither of these objects has zero net force on it. Okay, part C asks us to derive an equation for the acceleration. All right, so here is where we'll actually have to start using Newton's laws. All right, so let's look at block A first. Newton's second law says that the net force equals mass times acceleration, right? So the net force on block A is just going to be the tension. The two vertical forces cancel each other out, but there's nothing to cancel T. And that's going to equal the mass of block A times the acceleration, whatever that is. For block B, we do the same thing, F net equals ma. In this case, let's be careful here. B is actually going to accelerate downward, so I'm going to treat that as my positive direction. So the net force is going to be the weight, mbg, minus the tension in the string, and that's going to equal the mass of B times acceleration. So the reason I'm doing it this way is that I want to be able to use the same A in both of these equations. So these blocks are attached to each other, so they are both going to accelerate at the same rate. Technically, I would say the accelerations are not equal because that's a vector and they'll have different directions, but the magnitude will be the same. So if A accelerates at 2 meters per second squared to the right, B will accelerate at 2 meters per second squared downward. All right, so I have these two equations here, and I want to solve for the acceleration. So the way we do that is with substitution, we get rid of the other unknown that we don't want to leave in our equation is T. I happen to have an equation for T already, so I just take this and plug it in over here. So that gives me mbg minus ma times a equals mb times a. I want to solve for a, so I'll move the two terms with a over to the same side. And then factor out a. So this means the acceleration is going to be mbg divided by ma plus mb. All right, so that's one way. You might call it the standard way of doing this. Real quick, let me show you another way we can get this equation in fewer steps, but it requires a little bit of abstract thinking. All right, so here's my system here. So what if instead of writing a separate equation for each block, I just treated the two blocks as one system? The two blocks will have the same acceleration, so I can just write one equation for both of them. So this equation, the F net equals m times a. Now, I have to be careful with how I interpret this equation now. So the net force should be the net external force acting on the system. So these two tension forces are sort of internal to the system, and they end up canceling each other out, even though they don't point in the same direction. And that's because technically there's another force acting on the system from the pulley here, and it's really the three of those that cancel each other. So let's just consider the same forces that I included in my free body diagram up here. We still have this force ma times g and a normal force from the table. Those end up canceling each other out, so we just ignore them. But we still have this force mb times g. So that is essentially the net force acting on our system. It's just that one. So when I write this equation, mb times g equals mass times acceleration. So what is the mass? Now, my system includes both of the blocks, so the mass of my system is just ma plus mb. So the total mass times acceleration equals the net force, and you'll notice I've basically gone straight to this step right here. So we have our acceleration. Again, it's mbg divided by ma plus mb. All right. So that can be a handy trick when you're solving these types of problems. As long as all of the objects are moving together, if they're connected by, being tied together by ropes, they'll all have the same acceleration, so you can just write a single equation for all of them. Okay, so now we're asked, let's see, where are we? So part D says, consider the scenario from part A2. So that's where, what did we have? The mass of A is much, much less than the mass of B. Does your equation for the acceleration of the blocks from part C agree with your reasoning in part A? So in part A, we said that if the mass of A was much, much less than the mass of B, then the acceleration would be approximately equal to g. So does that agree with what we've got here? All right, let me actually copy this to a new page. So our acceleration is mbg divided by ma plus mb. So if ma is really, really small compared to mb, then the sum ma plus mb is not going to be much different from just mb. If you want to see this more clearly, put specific numbers in here. If this is 1 and this is 1,000,000, then if you add ma and mb together, you can just ignore the mass of A, right? It's tiny compared to mass of B. So that means our denominator here, we can just write it as the mass of B. So if we ignore the mass of A, we get mbg divided by mb, and our acceleration is in fact roughly equal to g. So yes, everything does check out. Our answer for part C agrees with our qualitative answer for part A. All right, so last part says that while the blocks are accelerating, the tension in the vertical portion of the string is T1. So now we replace the pulley of negligible mass with one that has a non-negligible mass. And now it wants to know how does the tension in the vertical part of the string compare to the tension in the horizontal part of the string. It wants us to compare the vertical tension before and after replacing the pulleys. Okay. All right, so in our first scenario here, we have some tension T1 pulling up on this block. In the second scenario, we have a very heavy pulley now. And we're going to have possibly a different tension force pulling up here. So this is the massless pulley, and this is the massive pulley. Now, a detailed analysis of this type of problem is definitely not AP1 material, but let's see if we can think about this qualitatively. So what would happen if we put a really heavy massless pulley with a lot of inertia here? Well, that pulley is not going to spin very freely. It's going to have its own resistance to this motion. So overall, we're basically adding more inertia to the system, so the acceleration is going to be smaller with the massive pulley. So knowing that the acceleration of the system is going to be less, is that enough to tell us the answer to this question? Well, if we focus just on the hanging block, there's still just two forces acting on that. We have MBG pulling it down, and then we have some tension force pulling it up. The gravitational force doesn't change from one scenario to the next. So how do we get the acceleration of block B to decrease? Well, there has to be more upward force. So in other words, if we're going to have less net force on block B, then that means there's going to be more upward force on block B. So that means T2 is going to be greater than T1. So the greater tension force pulling up on the block is going to result in a slower acceleration for the block, and that's consistent with what we would expect if we put a really heavy pulley into the system. It's not going to want to rotate quite as freely as the other one, so it's going to slow everything down. All right, so those of you who are taking APC next year, we'll come back to this topic and maybe learn how to analyze this in a bit more detail, but for the rest, you really only need to understand these qualitative arguments. All right, so that does it for this set. As always, let me know if you have any other questions. Thank you for watching.